part. That means it's the double reinforcement. For the double reinforcement, reinforced member, the basic formula is similar to the single reinforced member. The only difference is add this part, FSD prime, AS prime, and all inputs in these three equations we all found with D, AS, or E, capital AS, or AS prime. Basically, it is the same. As long as you remember this figure, the tension force is the same. FSD AS. FSD AS. So this figure is wrong, so some symbol is a mistake. So T is FSD AS. And for the compression force, we got two parts. One part is FCD BX H0 minus half X. This is the same as single reinforcement. Another part is beared by the reinforcement in the compression zone. This part is FSD prime AS prime H0 minus AS prime. So H0 minus AS prime, this is the arm for this compression force. For the compression force beared by the reinforcement in the compression zone is the FSD AS prime, this part is also this part, FSD AS prime. So the basic equation, these three equations, you should can write. You don't need to remember it, but you just remember this figure. You can write this down when you use it. That's the balance of the force, balance of the moment, the same as the single reinforcement. Just this part, we have more part for this. And for this double reinforcement beam, we have the same requirement for X, smaller than CBH0, the same as the single reinforcement beam. Also requires X smaller than CBH0. CBH0 is the boundary condition. Once X larger than this value, that means your design is over reinforcement. And also, in order to make the reinforcement reach its yield strength, normally we ask X larger than 2 times AS prime. So do you remember why we use this value? Why X should be larger than 2 times AS prime? Is there remember? So on this PPT, I don't put it here. You need to see your book, textbook. So this fictional S dash prime 00033 1 minus X 0 AS prime 2. Finally, we got this. Why we got this? Because we use this. And here we use because x equal to 0.8 xc. So this value. So see this equation. And remember why we say x should larger than 2 times as prime. Why? Why we see x should larger than 2 times as prime? You remember? Why? Yeah. Why we see in order to make sure the approximately comparison reaches the yield strength, comparison strength or yield strength, we need x larger than 2 times as prime. So why x larger than 2 times as prime? The reinforcement in the comparison zone can reach the yield strength.
The compression.
From this figure,
We use s equals 2 as prime, as prime because maybe the compression hasn't reaches yielding strength.
So see this figure, if you replace x by 2 times as prime, then finally you get the result So that's the reason why we see x should larger than 2 times as dash prime. Once x larger than this, then the result of the epsilon x prime will larger than this one. And also you should know the yield strength of the steel reinforcement is 0.002. Once the strain, this strain the reinforcement in compression, the strain reached 0.1, 0.002. That means the reinforcement reaches the yield strength. The yield strength is 0. The yield strength, this strain, not strain, this strain, every strength is stress. When the yield strain reach, then the stress and strain actually. So when the strain reach this level, that means the reinforcement reaches the yield strength. So that's why we ask the x larger than this, smaller than CPH0 is the same as the single reinforcement. And this one larger than 2 times the s dash prime is for the reinforcement in compression zone. Make sure the reinforcement in the compression zone fully used, reaching the yield strength. So we see the calculation method in this picture. I didn't give you the figure, but it's your book 16A, the calculation method. So So for this double reinforcement beam, normally also have two cases we need to discuss. So the figure 3 to 27. In this case, we are asked to solve the tension reinforcement AS and the compression reinforcement AS prime.
Which page was
6A. 6A. So for the calculation of this double reinforcement beam, you see this 6A. So in this question, we need to calculate the tension reinforcement AS and the compression reinforcement AS prime. So that means the reinforcement, we both the reinforcement don't know. Just hey, maybe we can just turn on. Yes, you're right. But it doesn't matter. Just okay, we see this. So for this case, double reinforcement beam, it asks you to calculate AS and AS prime. So of course, tell you the moment, the dimension. So just ask you to design how much we should put inside. So how to do this question. So we see the solution. The first step, assume AS and AS prime. So assume AS prime. So that means we got H0 minus E. The purpose of the AS is to get H0, the effective height. So once we got H0, we can use the basic formula, basic equation, to check the step B, to check whether it's a singular replacement or not. So how to check?
you have to find the percent.
So how to check is a singularly reinforcement or double reinforcement?
Yeah,
Should
you
we
can
find
see
the
it.
form of the moment?
Is the resist moment. If the resist moment calculated by the single reinforcement beam, the equation for the single reinforcement beam, if we use this equation to calculate the resisted beam MU, if this MU smaller than the gamma 0 MD, the moment induced by the external load, that means the single reinforcement beam is not strong enough to resist the load. Then you have to design double reinforcement beam. So in your book, gamma 0 MD, if gamma 0 MD larger than MU equal to FCD BH0 squared CB 1 minus CB. So how we got this equation? Why MU equal to this?
X, we know plus X by X equal. Actually, X equal H.
Because we use X equal to CB H0.
Yeah.
This is the boundary condition. So actually this is the H0 minus half X. That's it.
Yeah.
So this FCD BX, FCD BX plus, so MU equal to this. This equation is the basic equation for single reinforcement beam. And we use the boundary condition. The boundary height X equal to CB H0. Then, and this equation, the boundary condition, we got the largest resist moment of the single reinforcement beam. If this moment still smaller than the moment induced the load, that means single reinforcement beam is not strong enough. We have to use double reinforcement beam. So this is the step B. Step C. You see the book, they said we make the AS plus AS prime more economical because you have many choices. You have to, but the more economical choice, how to make this more economical. We still use X equal to CB H0. For the single reinforcement beam and the double reinforcement beam, actually the boundary condition is the same. They both use CB H0 as the boundary condition. Once X larger than this line, that means over reinforcement. X equal to CB0. This condition is suitable for not only single reinforcement beam, but also double reinforcement beam. We all use this boundary condition. So in this step C, X equal to CB H0 is the boundary condition.
Yeah.
And once we use this condition, we can make the AS plus AS prime the most economical. So save money.
Okay.
So at this situation, we can use the full in the book. There is a full use of tension steel reinforcement rather than compression steel. So firstly, you have to make the full use steel in tension zone, and then once this tension force not enough, they add, you use the reinforcement in comparison to help this section resist the force, resist the load. So at this equation, we can got the result AS equal to gamma 0 MD minus F C D B C B H0 square minus Q1 C B Fs D H0 minus AS dash AS equal to FSD H0 minus AS and D FSD dx so how we got this to result?
If the AS becomes big, meaning the AS prime will be smaller. If the AS, if it's big, meaning the AS prime will be small.
Yeah, if we use S equal to CBH0, this result, AS prime is the most economical result, and means the tensile reinforcement have been fully used. And can you know how we got this? Why we can write the equation like this? Just be, you see the basic equation 3 to 23a. Six seven page. The equation is 3 to 23a. 3 to 23b. Say AS prime AS. Because in this equation, we just replace x by CB H0. Then you can got the result AS prime and AS. See it? So that's why we got this equation. So to till here we have calculation the AS and the AS prime. Once we got this result, then the next step we need to select the diameter of the steel and the number of steel to get the real area of the tensile reinforcement and the compressive reinforcement. Just like the last class, we to check the table and select the different combination of the steel to meet the requirement of this larger than this value. So that's the step E. Select the diameter and the number for the steel bar. Then, as you have determined which type of the steel, and then you draw the arrangement. So 1 layer or 2 layer Well, after this, we go to the next step, check. This part is the calculation, so this question. After you have determined how to arrange your reinforcement, then you need to check if this design is okay or not. Because in this calculation, you assume some value, and this result is the theoretical result. Once you have determined the diameter and number of the steel value used, then you will go to the real AS X dash prime and this area of the reinforcement. Then you need to use this real value to check the construction requirement and the moment, the resistor moment, MU. If MU larger than gamma 0 MD, if this satisfies, that means your design is okay. And otherwise, you need to go back and change the value and calculate again. And also, we told you another situation. Let's see. Gave you the compression reinforcement AS prime. So the value of this will give you just ask you to calculate AS. So this is simple. So just do it is very simple. This one. At this situation, you just assume AS because you just assume AS, and then for basic formula, say x, you can calculate x equal to x0 minus this. Check if x smaller than c, b x0. If satisfied, not satisfied, so you need to modify design. So this solution is easy. So I will spend several minutes to see this question 698 to see if I have any question. To see if you can understand this. So meaning 69 page to see this equation 69 is for this situation. Everything I told you is included AS prime. Only ask you to calculate AS. Yeah, so how to calculate it? It's a little bit different with this situation. At this situation, AS prime and AS, you also need to solve. These two you don't know. And this situation can give you AS prime. So to say what's the difference? The step is different. So for this solution, the second solution asks you to calculate AS, and the AS prime I will give you to. So for this solution, first step is AS, assume AS. Once you assume AS, that means it is 0. You got
H minus S.
and then it's not V, you can calculate X. Because AS prime I have given to you, then use the basic equation, you can just get this x. So this x h0 minus
square root
h0 square
minus 2
minus 5cdb 2
bracket
0 md
minus
minus
f
f
prime AC
d prime a x prime h0 minus a x prime. So this result, do you know how we got this result?
then from this one.
Is to say in this equation there's no ax. We use ax prime. So C over the basic equation 3 to 23. 3 to 23, you see.
Yeah.
In the middle, 3 to 23a. 6, 7, 6, 7. So this basic equation, in the middle one, 0 to 23a, in this equation, we use as prime. There's no as. Because in this question, as prime is given to you. Then, in this equation, only x is unknown. And this, you see, is a quadratic equation. So this result is x equal to quadratic equation, x equal to b plus
4AC.
is this it? So we got this result. So this is the basic equation. You should use which one? Just because based on the condition I given to you. Because in this question, as prime is given to you. So that means you can use the second one. If the as given to you, then you can use the third one. Is this minus b? Is it?
Yes.
Minus b. I remember it's minus b. And when you check this, a little bit mixed. So this is the result. This is the condition. Give you as prime. Ask you to calculate as. Then first step, assume as got h0. The second step, use the basic formulation to get x. Once you get x, then we check if x smaller than CB h0. If this is not satisfied, that means your design is over development. It's not good. You need to modify the design. And then let's see if x satisfy this, then we can got AS, use the basic equation, the first equation. AS equal to FSD FCD plus FSD FSD prime AS prime. So is use the first equation 3 to 22.
And there is minus b. The quadratic equation.
Wait a minute.
The quadratic equation it is minus b.
X equal to minus b.
Minus
b plus. No. The quadratic equation. You were asking whether maybe there is minus or.
You just remove them.
Yes.
It's minus. Okay. Anyway, you know how we got this result. Let's use the basic equation. And then once we check x smaller than b is 0, then the first step, let's see, we use the basic equation to got AS. So, no problem with this, it's easy.
When will be given the AS time and we have to calculate AS, right?
Yeah. So, this situation, AS prime and AS we all know, then both this AS and AS prime we need to assume. And this situation, AS prime I give to you, we only need to assume AS. Assume AS, then got x 0. Okay. And then the step B, another situation, if x smaller than 2as dash, so x smaller than 2 times as prime, what that means? We ask for x larger than 2 times as prime. If x is smaller than this, what's this meaning? What's the meaning?
If x is less than,
Smaller than 2 times as prime.
that means
The x less than KCB is not satisfied.
The compression zone have not reached the dimension.
Yes.
This is the realistic, that's our problem.
So that means the reinforcement in the compression zone have not reached yield strength. The function have not fully used.
Yeah.
So at this situation, we how to calculate the AS.
Yes, equal.
If x is smaller than this value, we normally use x. We normally use x equal to 2 times as prime, and then by this value we can got as prime equal to kappa 0 md divided by f st h0 minus as prime. AS equal to this line. You know what?
From the formula.
Which formula we use?
3, the 3, yeah.
3 to 23,
Yes.
A or B?
What's A or B? No.
No, A.
A.
You sure it's A?
Yes.
Yes. Of course it's not.
Because the second one is 2 AS prime. So
Of course we use 3 to 23 B.
Yes.
Because we use this, then the first part becomes 0. Half x minus AS dash equal to 0. Then we got this. And another step, we calculated for the single reinforcement section, AS dash is not considered in the equation. So that means taking AS prime is equal to 0. Then we got another AS equal to FSD. LCD BX. Then we compare this, we use the meaning value of AS1, AS2.
Shush.
Okay. The following part is to check your design. So the first part is to check section check. Section check. Okay. And our book. ES and AS given.
Lordship, the page number 67.
69. So the main purpose is to calculate MU, the resist the movement, resist the loading capacity, to check MU if MU is larger than gamma 0 MD. So once you design, you finish your design, you determine the diameter reinforcement and the number reinforcement. Then you can calculate the real resistance force, MU. So now we need to check if MU is satisfied requirement or not. So this way you check AS and AS prime. You will also this equation. You can just use the basic equation to calculate MU directly. But for this, the basic equation is suitable for x smaller than say BH0 and let's have AS if you use the basic equation directly, x should satisfy this requirement. If x doesn't satisfy this requirement, how we calculate mu? So in our book, tell you how to do. If x smaller than x smaller than 2 times s prime. So that means the reinforcement in comparison to have not reached the yield strength. So at this situation, we just make it simple. We use equation 3 to 26. So to say, what's the 3 to 26? It's just we write here. We write here where is it?
It's a philosophy. mu equal fc.
Yeah. Right. mu equal to fct
A
fsdx fsdx and h0 minus dx dash. So how we got this? How we got this mu? I find it.
We take it from we take it from the formula 3
to 23p.
Yeah, 323A.
We just use x equal to 2 times as dash. Then the formula, the first part is equal to 0. Yeah, then we can go to mu. So if x is smaller than this, then we can use the maximum value 2 times as. So the result is you got, because it is smaller, this value, this mu, this value will be the largest, the maximum resistant force of this condition. Normally, for this condition, mu should be smaller than this actually. Actually, then we use this boundary condition. This mu is the maximum value for this condition can get. Any question for this? Okay. So another situation, if x larger than the CD H0, that means your design is over reinforcement. So for over reinforcement, how we calculate? One selection is to change your design, to make your design appropriate reinforcement. Another selection is just calculate the mu, use x equal to CBH0. Understand? If x large, that means it is over reinforcement. Some of the reinforcement are not fully used. It cannot reach the yield strength. Then we use this value x using boundary condition where we calculate this force. Actually, in your book, where is the part?
There was no part. They didn't write that part.
Actually, in your book, they didn't tell you this part.
Yeah. They didn't. They just said you use the basic formula.
Oh yeah, you in the second page, the 5 part, first step. if x larger than this, the design and the associated maximum loading characteristic modified. So we use the boundary condition taking into the basic formula. C equal to CB, x equal to CB H0. And for this condition, actually, your book tells another part. Once we got this, and also we use the singly possible rectangular section calculation the MU. This we call MU1 and MU2. Use FCD dx H0 minus x. This is the MU calculated by the single reinforcement beam. Suppose this beam is a single reinforcement. Don't care about the reinforcement. Don't care about this. Just use ES to calculation. Then compare these two. Take the largest one. And max, use the max. So this part is the section check of the double reinforcement beam. That means once you got this ES, S dash, S prime, we need to check this design if it's okay or not. That means we need to calculate MU to resist force. If this is resist force larger than the external force, then for the best situation x in this range, then you can use the formula physical equation directly to calculate MU. If x smaller than 2 times AS prime, then we can use s equal to 2 times prime, 2 times AS prime, got this MU1, and then we use the single reinforcement beam equation. We can got this MU2 and compare this two way, we can take the larger one. And for the situation x larger than CBH0 is over reinforcement beam, then we just take x equal to CB0, use the basic equation to calculate MU. Or another choice, you change your design to make its x smaller than the CBH0. So till now, for the double reinforcement beam, we have finished. The first condition is ask you to calculate AS, AS and AS dash. Calculate this. For this situation, you need to assume AS and S prime, and then got H0, got this MU. Finally, you can got this. So for this two different conditions, this condition AS and AS prime, you all don't know, and this condition AS prime gives you AS don't know. And the question is to us to calculate AS, and this is calculating AS and AS prime. So there's no very large difference. Just for the equation you use, a little bit difference. For this equation, for this condition, for this situation, you need to assume two small AS and S prime. And then once you got H0, we use this basic formula. How we got this formula? Actually, it's this one.
Yeah, we're gonna press H.
We use the boundary condition
Yeah.
x equal to
Yes.
CB H0. We use this condition, then we can got MU. Because in this everything is known. Then we can calculation AS and S prime. You see, this part, actually this part. So here all know, because this is the external load. This part is MU, and this part MSD prime is 0 AS prime. We all know. Then you can get AS prime. And AS is also the same thing. So in this condition, another actually is also sometimes assume x equal to CB H0. This condition. Use this condition, then finally you got AS prime and AS. And for this situation, AS prime I give to you and ask you to calculate AS. We also like this assume AS. Assume AS, we got H0. Once you got H0, you can use the basic equation, product equation to got this result x. And then based on the value x, if x satisfies this condition, you just use the basic equation to get AS. If x is smaller than this, we got two value and then use the minimum value. Say if x is smaller, normally we use x equal to this one. Okay? This is for the single reinforcement beam. We calculated this one, this two, we got this minimum AS. And also for this situation, we can find if x is larger than this one, that means it's an over reinforcement. Actually, normally you need to change your design. Or we use this same thing, use this x equal to CBH0 to calculation. But it's new. Normally, if you find x is larger than CB, that means your design is not good. You better go back and change your size, change the material, something like that to make x smaller than CBH0. So this is the basic equation. Now if you close the eyes and thinking condition, for this solution asks you to calculate AS and AS prime. So thinking how to do it step by step. And this solution, think one by one step. Can you just remember, if you don't see this, can you remember how to do this?
Yeah, a bit. Now see, this one is when we don't know AS and AS prime.
Yeah.
But this one is when we know AS prime.
Yeah.
And we don't know AS.
It's different, you see. In this we calculate x. In this we calculate mu. So that's difference. So now we remember it. Okay. I give you some homework.
He has already taken it. He'll put it inside the group. Okay.
It's your job,
And this is the second homework. The double beam, the second size, and the calculated movement MD, one factor concrete say 25 and give you AS and S prime. Then check if this design is okay or not. So the first question is the calculation, the second is check.
So, the purpose of
Camera action. This is first part.
Or you can choose do this on this blackboard. You can try. You can find it.
Largely.
Yeah.
This means AS and AS prime.
Yeah. S prime. So we have break.
Okay, largely. 무창가.
my time is not Buchanga, it's Busanga.
무창가.
I want me to arrest you.
Reinforcement and the concrete no longer resist the tensile force. So the concrete intention has no contribution to load carrying capacity. So this part tensile concrete can be drained and take away. Then steel reinforcement can be placed in the refined concrete area. As a result, a reinforced concrete T-shaped beam resting is formed. Its load capacity for T-beam is the same as the rectangular beam, but by this way, we can seal the concrete and reduce the weight. Because for this rectangular beam, once the concrete crack, actually this hard concrete is no longer used. The force we see, we just transfer to this reinforcement. So this hard concrete actually is no use for the loading carrying capacity. Then we try to remove it just like this, something like this. Then generally we got this T shape. Of course, as you go up, make this T more, because when the force increase, the compressing area becomes smaller, something like this. Then, compared with the rectangular shape, we just remove this part and put the reinforcement in the bottom. So the rib of this T beam, the main function is just to place the reinforcement. And the up part, of course, is to resist the compressing force. So from the rectangular shape to T beam to T shape, the resistance or the load carrying capacity actually no change. because the compression area is the same as the rectangular shape, and the reinforcement is same. But we removed a lot of part of the concrete. That means the self-weight of the beam have been reduced greatly. Then the self-weight has been reduced. That means we can make the span longer, because we know normally nearly 90% of the loading capacity is used to resist the self-weight. If self-weight was reduced greatly, of course the span can make it longer. So that's why actually T-shape beam is come from rectangular shape. That's based on this load distribution, tensile force and compression force. So you see, for the normal T-shape, the tensile force is resisted by the reinforcement. The compression force is resisted by this part. Sometimes it's resisted only by this flange part, or sometimes it's just the rim, part of the rim. And this is the inverse. The top is in tension and the bottom is in compression. You see, this situation actually is just like the rectangular shape. No matter if the shape looks like T, but if suppose at the middle point of the continuous beam, the beam is bearing negative moment. The up part is in bending, the lower part is in compression. If you use this T-shaped beam, then up part is in tension. The tension force is resisted by the reinforcement, and the lower part is in compression. The rim bearing the compression force. Actually, this flange, once the crash occurred, the concrete of this part, we just neglect the tensile force beared by the concrete. It's very small, and all we treated it as all the tensile force transfer to this reinforcement. So for this solution, actually, it's just like this, just like a rectangular beam. No matter if it looks like a T-shape or not, actually the work just work as rectangular. So for this solution, it's just like this, So if we don't see this, we don't consider this part actually. So this flange have no use actually for this situation. It's just work like this rectangular shape. So also it looks like T shape. Actually it works like the rectangular. The formulation actually is similar. So in your book, there's some of the content introduced about the equivalent shape, equivalent change of this shape. But this is very real use. Maybe we just introduce since your book has talked about this, we just introduce a little bit. So in our book, we introduce this shape. plate with an empty hole. So for this type of beam, this section rectangular with two hole inside. It's not easy to calculate the force. So we try to think to make an equivalent shape. In our book, they make this equivalent. And finally, they make this something like this I shape. So from this rectangle, the hollow circle, and then to this shape, and the equivalent. We call this equivalent. So how to make this equivalent cross section? Because this time is easy calculation, but this one got this circle is a little bit complicated. So in order to use this section to replace this section, they make sure the area of this hole is the same, and the initial is the same. The equivalent area and the equivalent moment initial. Besides this, B K H K equal to 4 square. This area, this B K H K B K. So the area of this square is equal to this hole, and the moment initial B K H K equal to, so this, the moment initial for this is equal to this one. See, by this two formula, we got this HK equal to BK equal to, then finally I got this. So the basic principle is if the area is the same and the moment initial is the same, then we can change this section to this section. Which one? Yeah. This area was like BKHK equal to the area of this circle. And this moment initial, this formulation, for this rectangular shape or square shape, the moment initial is this equation is one big equation. in your material mechanics. So this was a small part in the content on your book. It just introduces the equivalent section, how to calculate the equivalent section. So why we transfer this section to this section? Because for this section, actually this section, the calculation we can use the T shape or rectangular shape the equation to calculate the loading capacity, the moment of the mass. But for this, see, it's a little bit difficult. It's circle. So for the height or for the effective height, H0 or AS, it's very difficult to calculate. It's not uniform. So for this shape, it's uniform distribution. So we can use this shape to calculate the loading capacity for this, use this equivalent shape to calculate this part. So that's why we use this equivalent section for this circle section. So another content on our book is the determination of the effective width BF prime for the compression flange. So why we introduce this? Because for the real situation, for this TB, the up part is in compression, but the real distribution of the compression actually is like this. So that means the compression stress is not uniform along this fringe. So that means if you want to calculate the real compression force, it's not a little bit different. It's very difficult. Just like this. For the rectangular shape, we see the real distribution is the circle. But for this flange, in this y direction, the distribution actually is also near the rim. The compression force is larger. And go to this direction, go to the edge of the flange, the compression force generally decrease. You just imagine it's T-shaped, and if you bend it, of course at the side, the force is smaller, in the middle, force is larger. So it's not a uniform distribution. But for this curve, if you want to get the compression force, of course, you need to use the integrate. It's difficult. So for the project use, we want to make it easy. Normally, for this top shape, remember we use this equivalent rectangular stress block. And for this, we also make this equivalent once BF. To make this value is equal to the real distribution value. Just to make this calculation simple. So now the question is how to calculate BF BF, book is BF prime. Something like that. So for this curve is the real actual stress distribution. Now we want to get this equivalent watts BF prime. Use this rectangular shape to replace the real distribution. Keep the total force is the same, but make the calculation simple. Now the question is this BF prime. How to calculate this BF prime? This flange effective wise. In the design calculation, you want to facilitate the calculation according to the principle of equivalent force. Equivalent force, that means the action point and the total value of the force keep unchanged. So flange watts of the beam rate working together is limited to a certain range, which is called the effective watts BF prime with compressing flange. Within the range of the flange, it can be considered to be all involved in the work, assume that the compression stress is uniform distribution. Then I didn't put in this PowerPoint. In our book, introduce the 3 different situations. According to the code, see your book 72 page 72. So the first situation for simply supported beam, 1/3 span is used. So if the bridge or structure is simply supported, then 1/3 span is used. So what's the meaning of 1/3?
1/3 span.
So like this. This is the span, calculation span. 1/3 span is not the span of the bridge. It's the calculation span of the TP. So 1/3 span is used for positive bending moment range of the initial span of the continuous beam. 0.2 span is used. And for positive bending moment range of the side span of the continuous beam, 0.27 span is used. So different situation. This BF dash is different. BF prime is different. And then the second part is the average distance between 2 adjacent beams, or average distance between 2 adjacent beams. Use this way, or the third situation, B plus 2BH plus 12HF dash. This, see your figure 3 to 31. BH and HF prime have different meaning. So different conditions can use different values to calculate this BF prime. In our book, we tell you three different situations. You can calculate BF according to this. So we see the basic calculation formula and application condition for T-shaped beam. For this T-shaped section, it's mainly can divide into 2 categories. based on the height of the compression tool. One is compression area is in the flange thickness, just like this. Only in the flange, this flange or the plate or the flange in compression. Another situation is not only the flange but also the rib. The rib is part of the rib is in compression. So you see this situation. If only the flange in compression and the tensile force is resisted by the reinforcement. So you see this situation is just like this rectangular shape. Just like this rectangular shape, you see. So this type of T shape actually is just one type of the rectangular shape. But if the rib in compression tool, so the compression area is basic shadow region. So it's a difference with the rectangular shape. So that's two difference. So this type the T shape is really work as T shape. But this type of T shape actually is working as a rectangular shape. So it's not because it looks like T shape or rectangular. You should see the real action situation or real working situation. For this type of T shape, its real working condition is just like the rectangular shape. So the basic equation you can use the same as the rectangular shape. But this one, the basic equation is a little bit different. You should add this part, compression force. So you see, basic formula for the flexible capacity of T shape for the first kind. The compression area just in flange. For this part, you see, the basic equation is the same as the rectangular shape. Just the watts is a df prime. The height is the same. So all the difference is just the watts. The watts is the equivalent watts. And this equation actually is the same as the singularly reinforcement rectangular shape. So only the difference is this BF is the equivalent watts for the flange. This equivalent watts we can use the key code to check different type, use different watts. So this is the basic equation for the first kind of T shape. The compression area just in flange. And for the second type, if the T shape, not only the flange but also the rib is in compression, then the force, the equation, a little bit different. Just because the compression force, not only this part, also include this part. If we suppose this height is x, then C1 FCD B, this B x. So this figure, some symbol is wrong. So just go here. This E, if this is in compression, this is the BF. You see, C1 compression force 1 equal to FCD BX. So this part is the force induced by this part. And C2 FCD H
F prime.
F prime and BF prime minus B. So this part. So this the C1. This part is C2. And the T force, tension force, the T is the same. FSD ES. So the basic equation become C1 plus C2 equal to T.
So this diagram is wrong.
What?
The diagram.
This symbol is wrong. But this equation is correct. Just because you see x is the height for this from the neutral axis to the up part, this section, say like this. This is for the force balance. And for the moment balance, FCD BX H0 minus half x is the same. FCD BF minus B HF H0 minus half HF. So this is because the comparison force we divide into these two parts. The first part is this part, the moment induced by this force. And the second part is the moment induced by this part 2.
So the moment induced by the part 1 is the FCD.
Which one?
The one.
Yeah.
The one.
So the moment induced by this one, FCDBX, H0 minus half x. Because the arm of this part, the arm is from here to there to the ES.
To the tension part.
Yeah. So here, so there, here is the fifth. This AS. And this part is the half x. From here, half x to here. H0 minus half x.
Okay.
So this part is the C1. And C2 is here. C2, the arm of C2 is larger. H0 minus half HF, because this HF prime. HF prime is the height of the flange. So for those basic equations, you don't need to remember. You just remember the figure. Just know the symbol for the different dimension. Then you can just write it correctly. So for this second part, we'll teach it basic equation, force balance, moment balance. Now you just close your eyes and you think about this shape. Every part. If you don't see this, and write out this formula. You can?
Yes.
Okay, you try to go back there to write that. Okay?
Okay,
You can try?
I can try.
Okay. You write the movement, the balance of the movement. And draw the figure first and write down. HF prime.
No.
Yes,
So C1 plus C2.
C2 is wrong. You
A-
see,
AC2.
A0 minus half x. What is A0 minus half x? C2 is a compressive force.
there is time here.
No.
This means
You see, for this part 2, how to calculate the area of part 2?
Area of part 2.
Yeah, the two sides flat, the flange.
The B prime F
Area.
minus B.
The area we think is
Yeah, area this part and this part of part 2.
two part. This is up and down, right?
this one.
Yeah, and this one, yes. How to calculate the area of these two parts?
We take HF as
Yeah. And the mass?
In the width, this part, the B. the B from
This B,
yeah.
this B.
The total
B
wife
prime
of
F.
friend is BF prime.
Yeah, BF.
The total ones.
minus the B. The B from the side.
That since medial B will be minus, right?
So the area of these two parts, how to calculate?
Are we take this one times
Yeah.
this one?
According to no.
No. You won't use it to times it. It will just be like you bring the bracket and it will be B prime F minus the B. This.
Oh. Oh, okay.
Yeah, minus B.
Yeah, this prime. They make the balance of the moment.
Hey. Why don't you just put it into the T equals C1 plus C2, then you just put in the formulas.
So the arm of C1, the arm of C1.
The arm of C1 now is this one.
Yeah.
And the arm of this one.
The arm of C2 is the arm of this one is okay is this minus x okay is I will take I know that here it should be minus. Here it should be is this from here is okay. X.
No, it's right. Yeah, finally, right now.
Okay.
Yes, it is. So you have to write it yourself. Maybe you just remember it's not so deep.
We have to write first one. Then first one is we have to put and second one. The second line.
Yeah.
need only this one over this.
So you think it's very simple. When you write, you find it's not.
That means we have to write this one and that's one. This one first and second one.
Yeah.
We have to memorize this.
This one is a great, yeah, this is simple, yes.
Understand?
So we agree?
Okay, that's
Then we need to calculate AS. So how to calculate AS? Actually the same. Say if you do the solution, first step assume AS. So the effective height is the same as the rectangular shape. Normally in your book I told you different type of the structure AS. You can use different value. You see in your page in the book 74. For the hollow deck cross section, failing steel plating will be often used. The work can be conducted according to the equivalent lower flat thickness F. In actual cross section, arrange one or two layers of steel. Accordingly, they smooth the issue. For precast casting inside TB, where the steel plating is often used, due to the height of the multi-layer reinforcement is not more than 0.5 to 0.2 H. We can assume AS equal to 30 plus 0.07 to 0.1 H. So for different structure, given the splitting of the reinforcement, AS you can just use different value. Then the second step, determine the effective width flange BF. So this is the difference with the rectangular shape. For T shape, we need to determine the effective width of flange BF prime. So how to determine this BF prime based on CHBC code? The case can consider taking the minimum value. So this three condition in your book 72 condition, three different condition, you can get different value, then choose the minimum one. So once you got BF prime, then the other step, determine the type of the T shape. You should determine whether is the compression just the flange or whether the rib is in compression or not. So just determine whether this part of the rib is in compression or in tension. If the rib is in tension, this means the compression area is just in this flange. So that means it belongs to the first kind. It's work as the rectangular shape. If the compression is coming to this ring, then it's the second type of T shape. The equation is just now right there. So because why we need to determine the type of the T shape? Just because the basic equation is different. If it's just the flange, the equation is just like the rectangular shape, it's simple. If compression is a rib, the equation is a little bit complicated. So the reason why we determine the shape, the type of the T shape, is just because the equation is different. So how to determine, how can know it's a type 1 or type 2? how to calculate this? So use this value. We just suppose the compression area, the height equal to HF. That means the total flange is in compression. So at this situation, the resistor moment. You see, if this resistor moment big enough or not. If this resistor moment induced by this compress is bigger enough than the MD, than the external load. That means the compression is just in the flange is enough. Then this situation is belong to the kind one. If this flange is this force, if the flange, total flange is in compression, the moment, the resist moment is not enough. MU is still smaller than MD. That means only this in compression is still not enough. Then part of the rib is in compression to resist the external load. Then that situation belongs to the second two, the second type tissue. So we use this formula L. Suppose X equal to HF prime, then the moment induced by the compression force, we can calculate and use this formula and compare this M with MD. If this M is smaller than MD, that means if M is smaller than MD, it belongs to the first type or second type. If M this moment smaller than gamma 0 MD, smaller than gamma 0 MD. So this T shape belongs to which one? Type 1 or type 2? Which one? Smaller than MD. This M actually is MU, the resistor moment.
Type 2.
Think about it.
Resistor moment. Small. Oh, if it's small.
Yeah.
If it's small, it's like one. That one. That two.
If it is smaller, if MU is smaller than gamma 0 MD, that means only this flange in compression is not enough. Part of this ring also should be in compression.
That.
It's type 1,
That two.
type, yeah, if the gamma MD is less than
If
compression.
this MU smaller than gamma MD,
Oh, if this one is smaller than gamma MD.
yeah,
That two.
and 2.
That two. Because that one should be
Yeah. That one
Yeah.
is type 2.
So you should understand it, not just remember it, understand it.
Okay.
So by this equation, we determine whether it's type 1 or type 2, because type 1 and type 2, the basic equation is different. And then for first kind of type 1, taking BFH as a rectangular cross section, because type 1 actually is just if we just say this type, it's working like as the rectangular shape. It's just working like as a rectangular shape with the y BF prime. It's just like this rectangular shape for the type 1. then the height of the compression to x we can calculate it. Because for the type 1, the x is in the frame, so the z value or x you need to calculation. So we got this value x equal to c h0. C equal to this. Do you remember this equation? It's just for the rectangular, single reinforcement rectangular shape. So we can use by this equation to got calculation x. So once you got x, then as you can use this equation. As is you can get. It's easy. And for this second type, for type 2, you also need to calculate x. But the little bit difference is c is difference. So what is the difference? This c is the result by the quadratic resolution. It's just because it's from this formula. So anyway, we have to calculation x. And once you got x compared with this, x should be larger than, for second type, of course x should be larger than hf prime. And CB is 0. We need to check if x smaller than this. If this x satisfies this requirement, then we can use this equation, just calculating the moment and calculating the AX. Use this calculating AX and use this calculating the moment. If it doesn't satisfy this condition, or if x larger than CB is 0, then the design is need to be modified. That means it's an over reinforcement. So all the basic equation you only can use x satisfy this requirement. Then you can use the basic equation. If x larger than CB 0, the basic equation is not useful. Is not satisfied. So this is the calculation. Just like the rectangular shape, we need to check. After you calculating, you need to check. So the condition is giving cross-section area, tensor reinforcement layout, cross-section dimension, and material strength. Angle is cross-section fractal capacity. That means MU. You need to calculate MU. So checking whether the reinforcement layout satisfies the specific requirement or the construction requirement, and then determine the effective Y of the flange BF prime, the same as the calculation, and then judge the type of the T shape. See, here is the difference with just now. Just now when we calculation, we use this equation to determine whether it's type 1 or type 2. And now we use this equation to determine whether it's type 1 or type 2. What's the difference? See, this part is the tensor force. This part is the compression force. So if this compression force is smaller than this, that means not enough. You have it's belong to second type 2. So here we use the force compared by the force, tensor force and the compression force. And just now we compared by the moment. But why here we don't use the force? Because here we don't know AS. Here we know AS, so we can use the force to determine whether it's top 1 or top 2. So that's the difference.
It depends on the.
Yeah, at the first, when we calculate it, we just know the compression force, the arms, then you can use this to compare with the moment, determine whether top 1 or top 2. But now, everything I told you, just to check it, then you know the tensor force, you know the AS, that means you know the tensor force. And then you know this compression force, just compare this. If smaller than tensor force, that means only fluid compression is not enough. Part of this range also in compression, that belongs to type 2. So that's two different methods to determine whether it's type 2 or type 1. So when is the kind 1? MU is easy, just start with the rectangular shape. And when to section 2, the same thing like this. So this is all this basic equation we need to use. But for this T shape, you see for the time, we got this example on our book. So it's better to see this example to just go through this example to see. So because the equation, the basic equation is simple actually. Only you use it, you just use the calculation, then you can just make one.
Actually, see, in this equation, see what they wrote under. That is to say, the tension of steel reinforcement, FSDAS, is less than or equal to.
Yeah.
But it's not less than or equal, it's greater than or equal to.
No, you just compare this one compared by this, compare these two. You don't see the symbol. They say if this one is smaller than this one.
Okay.
If it's smaller, that means it's type 1. If it is large, it's type 2. So on our book, we got this example. Actually, we can change some way and make it as a homework. See your book. See your book. The example is 60. Is a prefabricated simply supported the T-beam. Section height is equal to 1.3 meter. Effect wise PF prime equal to 1.6 meters. And C13 subconcrete HIB 400 steel bar. So now, if we change some value and make it as a homework. So we can use the concrete C40 and reinforcement HRB 335 and MB equal to 3. So check these 3 conditions. You can do it in just just see this level and do it again to see. You see the example. So the first section design, the first step calculating H0. Due to the weld steel security, set AS equal to 125 millimeter. So how they got 125 millimeter? You see this 74 page. AS normally 74 and the 74 and the end of the page and the bottom and the lower part.
Okay.
Normally AS equal to 30 millimeter plus 0.07 to 0.1 H. So this you see normally before we do the rectangular shape, we normally would assume AS equal to 44, 45, something like this. But now you see, they assume AS equal to 125 millimeters.
74.
74. Here, assume equal to this. So that's the why they assume AS so large. Why we don't assume AS equal to 45 or 50? They assume AS 125.
Yeah, it's not written because it's 145. It's not written.
Yeah.
So what? I will just follow. We assume, but here they assume bigger.
Yeah.
145.
45.
145. Yeah. Why is bigger? Why is not 45 as we was assuming?
We got a many layer of the reinforcement normally. If you only just because for this T-shaped beam, you should notice. You should notice for rectangular shape. This B, the wide B is wide enough. You can put a lot of reinforcement in one layer. But for this T shape, you see, this B is so small. You have to put it into lots of layers. So that means AS is more larger than this one. Normally in rectangular, maybe just one layer or two layer. Maybe in T shape is 5 or 6, even 6 layer. So that's the difference. Why the AS is larger?
Okay.
Because they use this AS equal to 30 plus 0.7 or 0.1 H. See, H. So that's the all content of this chapter 3. We finished chapter 3. Next week we are going to reduce chapter 4. And you do this homework to see if you have any question or not.
And now, should we after chapter 4, we see